Hello, this is part 2 of the lecture on quantitative analysis methods. Now I'm going to talk about how we can address the problem of inferential statistics. Whereas descriptive statistics is about describing patterns that you see in your data, in the sample of data you have, inferential statistics addresses the question of how likely it is that patterns that you see in your data also continue into the population. And in order to address this problem, what we need to do is to get very good at studying these patterns in the data. So the link is that descriptive statistics helps us look in detail at the kind of patterns you get in data, so we can tell how likely it is from what we've seen that the pattern will extend into the population. And the name that we give to patterns occurring in data, in statistics, is distributions. So we're going to look at some distributions now. Now, here I have the data that I showed earlier on land holdings in 4 areas. Now, in Excel, it looks like this. So this is the data in Excel that I worked with before. And if you transfer this to the Specialist Statistics Program, SPSS, it looks like this. And you can see it looks pretty similar, except that instead of these labels here being in the sheet, the only thing that's in the sheet is the data itself, numbers. The variable names become incorporated into the column headings here, which both gives it a lot more power because here you concentrate on the data analysis and makes it slightly less flexible for general data manipulation. So it's still worth having things like Excel, even though, as we'll see, for statistical work, this is far quicker. Now, what we're going to do to start is explore these 4 sets of data on 4 areas using a command called explore. I'm going to take, these are the 4 variables, land holdings areas A, B and C. We put them all into what's called the dependent list. So this is the variable that's going to be analysed. We're going to ask it to give us both statistics and plots. I'll leave the statistics options as default. On the plots side, I'm just going to specify histogram. This is just being shown to you for demonstration purposes. We're not going to expect you now to be able to do all this stuff. But in future, if you do want to use any quantitative analysis in your projects, then I'd suggest getting hold of SPSS, which is available at discounted, or really available free as members of UEA. So what we get from this. Some previous results of this. Now here's the results we get. So what it's done is, first of all, the statistics, it's given us a set of descriptive statistics for areas A, B, C and D. And as I see, it's actually given us all the statistics we've worked on so far in this whole lecture, plus a whole load of others, all without entering any formula. It's just churned them all out. So much easier than do it in Excel. Here are the means for each one. So that in area A, mean land holding is 1.22 hectares, and area B it's 4.92. The medians are 1.2, 3.2, gives us standard deviations as well. And a number of other things, gives us things like range, the interquartile range. So all of it's done automatically. Now beneath here we should find that it's done some histograms as well. So here's for area A, here's the histogram. And what a histogram is it puts it into categories. So this is between about 10 and 10.1, 10.2, 10.3, 10.4, 10.5. So between 1 and 1.5 hectares, there's, that'll probably be this bar here. This is how many households have that much land. Between 0.3 and 0.4, only about 2 households. Between 0.4 and 0.5, about 6 households have that much. So when the taller the bar, the more households have that range of land holdings. And here, area B, quite a different kind of shape. And area C, again, quite a different kind of shape. Now I've put these back on a slide over here so we can compare them all together. These are what I created earlier in SPSS, area A, B, C and D. Now the names that we give these patterns is, and it's quite hard to draw, I'll get the computer to draw these properly in a moment, but it's a pattern that characteristic in statistics is this sort of a pattern. So the areas in the middle, the most average areas that most people tend to have, are in the middle. And then each, as it tails off, a few people have got a small amount of land on this, a few people have got a small amount of land on this, but not so many. But the point about this one is that it's kind of more symmetrical. The distribution, the pattern of the way that the land holdings are spread out is quite symmetrical around this central point here. And this distribution you could describe as symmetric. This one's actually kind of similar. This one's, no, I can't quite draw it as such, it's fairly symmetric. The ones that are different are these. Let's just label that as symmetric, lest there be any doubts. These, however, are not symmetric. In these, there's a few people have got no land. This is probably the 0 to, it's hard to read the labelling, but 0 to 1 or 0 to 2 here in this first category. Quite a lot of people. A lot of people have got very small amounts of land. Quite a few people have got this amount. But then, as you go into larger and larger land holdings, there's just a very few people who've got these very large land holdings here, and one person has got a really enormous land holding here. So it sort of tapers off very, very gradually as you get larger and larger. So the shape here is it goes up from 0 very, very swiftly up to a peak at a very low level, and then tails off like this. And this kind of shape is called non-symmetric, or more commonly skew. This is a skew distribution. Skew. This one down here is also skew. Now, because it goes like this, the tail is on the lower side, and then it builds up and comes down, oh dear, very sharply like that. Now, seeing as both of these are skewed, we need to have some way of distinguishing them. This one is actually known as a positively skewed, positive skew, and this one is called a negative skew, or negatively skewed. There are different ways of remembering which one is which. If you're very into mathematics, then you can look at the third integral of the moments about the mean. Will come up as positive here, negative here. If you're not really into that kind of advanced maths, and you just want to remember which one's which, if you turn this on its side, this shape, you'll get a letter P. And the P means a positive skew. If you turn this one on its side, you don't get a letter P, so it must be a negative skew. Unfortunately, it doesn't give you an N, unfortunately. So remember, that shape, turn on its side, P, positive skew. If it's reasonably even each side, then it's symmetric. We go back to Excel and redo some of these charts. I'll just do one of them. If I redo the histogram for A, using the special histogram command, there's an option here to display a normal curve. And this is quite good at giving you a sense of how close it is to what's called a normal distribution. Now, a normal distribution is a very special kind of symmetric distribution, which we'll talk about quite a lot, and you use quite a lot. See, that's an exact normal distribution. It's not quite fitted, it's sort of almost approximately fitted. Now, part of the problem here is that there are not that many landholdings. I think there's about 200 observations. And with only 200, it's hard to see whether or not a full population, which could be thousands, would actually fit it or not. It's hard conceptually to tell whether it's really a normal distribution or not. Now, because of this, that is the theory of things like normal distributions, is based on the idea that the population really is very, very large, almost infinite or millions. So you get these very nice smooth shapes. And to try and give you a better idea, we have these populations. Now, in these populations, we're dealing with the topic of pollution. And we have 3 different sorts of pollution. And the figures here, this is for pollution type 1, these are figures per parts per million. So there's 370 in this location here. This refers to different locations. Here it's been measured, location 1, 3,789 parts per million of this particular pollutant. And population 2, much lower levels, 82, 90. Population 3, sort of somewhere in between. And the point of these partly is that there are just loads and loads and loads of different places. So we have measurements of this pollutant level at 10,000 different locations. Now just looking at this pollutant number 1 for a start, we can look at all of them. I think we've got this data in SPSS, so along with some others. So the first 3 here we're going to look at. Pollutant level, pollutants 1, 2 and 3. Now, if we do the explore command again, okay, I've already put those in there. We're just going to look at plots, just histograms. And here they are. And hopefully you can see that this is pollutant number 1, number 2, and number 3. Now we've got 10,000. You can see it's starting to look much smoother. Those 2. You should be able to recognise that this one is quite symmetric. This one's quite symmetric. This one definitely not. This is a skew. Can you remember if it's a positive skew or a negative skew? Now to check whether this might fit the special kind of distribution, which we call a normal distribution, we can do that graph again. It's already done, normal curve. And you can see it's really quite a close fit. So pollutant 1 does follow a normal distribution, and in fact pollutant 2 does as well, this one. But pollutant 3 doesn't follow a normal distribution. This is skewed, and in fact it's positively skewed, because if you turn that on its side you'll get a P. Now finally, if we go on to, I've transferred these back into the PowerPoint. This will put to one side this positively skewed one. Oh, can't even draw it. Turn it on its side, you get a P. That's a positively skewed. These 2 here are actually symmetric, and they're normal distributions. Both have normal distributions. So they're the same shape, exactly the same shape. The only difference in them is that the level, see the level here is much higher, 3,500 compared to 80 or 90. That's reflected by the means. And SPSS actually gives you the means up here, so 3,000 odd against 84. So you can tell that pollutant 1 has much higher level in general, and also it's more spread out. It's measuring how spread out it is this way. So the standard deviation is telling you how spread out things are from the mean. If you remember the numeric exercise we did earlier, go through every single one of these and work out how far it is from the mean, and we square it and so on. So the standard deviation is telling you that pollutant 1 is also more spread out, because this one's bigger than this. But it's not quite enough to know that standard deviation just tells you how spread or unspread the population is. We need to know a little bit more about what exactly standard deviation means. And that's what we'll look at on the next slide. What does standard deviation actually mean? To understand a little more about what standard deviation tells us, I'll look at these examples of pollution concentrations. Now here's pollutant number 1. Here are the different concentrations at different locations. If I enter a level in here, such as 3,300, this computes that in 2,506 locations, the level was below 3,300. Now we can check that directly by sorting all these into order. And I can see visually then 3,300, I track that down, it's round about here, 2,500 or so, between 2,502 2,509. So 2,506 is coming out, that's in the middle. So that's the number of locations where the pollution level is less than 3,300. So we don't have to, there's no need to do this visually each time. We can just rely on this to count how many locations have less than this amount of pollution. 2,500 out of 10,000 is 0.25, about a quarter of them. And you can see that this is below the mean. If I put exactly the mean in, 3,474, should be around about 50%, because you're right on the mean. So about 5,000. Now to try and get an idea of what standard deviation means, we can take this figure, which is the standard deviation for this population. Now what we're going to do is we'll treat this as a unit, a single unit. And we're going to treat this as the starting point. So if we start from here and go up 1 unit, where do we get to? Well, what we're going to do is put that value here. So we clear that. We're going to start from the mean and add on 1 standard deviation. Mean plus 1 standard deviation takes us up to 3,732. So that's that plus 258. Okay. Now this is telling us that there are now 8,419 locations with a lower concentration than this, which is the mean plus 1 standard deviation. 8,419, well, so what? But let's go to another population here where we know that this is normal and see what happens here. If we start from the mean and add on the 6, so it's going to be about 90, 84 point something plus that. So start from the mean, add on 1 standard deviation, comes to here, 8,446, 84 or 0.8446, 84% again. Very similar to that one. Quite a pattern. 84% in each case. Not exactly the same, but very close. Try and population 3, going, start from the mean, add on 1 standard deviation. It's 157, but now it's 86% or less than that, so it's different. And of course, the difference is that the first 2 populations are normal. This one's not normal, it's positively skewed. And that's why this comes out slightly differently. If we could summarise what we've found here, we found that here are the different means, they're all very different levels. Standard deviations, all the populations have different spreads. But if in each case we go 1 standard deviation above the mean, we find that in cases A and B, almost exactly the same number of locations are below, and as a percentage, it's almost exactly the same. Does not work for population C, only for A and B, who are normally distributed. That's what happens if we go 1 standard deviation above the mean. Well, we're not limited to that. Instead of going 1 standard deviation above the mean, so here, we could go 3 standard deviations above the mean, or 10, or 1, or 1.5. So let's try going 2. So we start from here, add on 2 times the standard deviation, so it's about 500. That takes us up to nearly 4,000, and there's 97.87% of the locations have less than that. We're getting quite high now. So 97% have less than that. Let's try doing the same thing in population 2. mean plus 2 standard deviations takes you up to 97, and 97.97% are below that, 9,797 of the 10,000, which is really very close to the result from population 1, even though the size of the numbers, the spread of the numbers are very different. Of course, when it comes to number 3, it's probably not going to work because it's not normal. No, it's not. So it doesn't work for that again. So this is for 2 standard deviations. Start from the mean and go up 2 standard deviations, so these places here. In cases A and B, got almost exactly the same number, which works out as the same percentage, very closely. 97.87, 97.97. Population C, it doesn't work. They're not limited to 1 or 2 standard deviations. You can go any number. You can go half a standard deviation up, 10 standard, anything you like. A particularly useful one that's often used is to start from the mean and add on 1.63 or 1.64 standard deviations. So start from there, add on 1.63 times the standard deviation. So the standard deviation is like a unit saying how far above the mean you're going to go. 3,894. The special thing about this is that there's 9,494, which is pretty much 95%. And if you try it in population 2, yeah, again, pretty much 95%. Population 3, it doesn't work. Let's just show you the results. So if you go 1.63 standard deviation above the mean, in populations A and B you get pretty much exactly 9,500, pretty much exactly 95% are below that level. Doesn't work for population C. So you can predict the level that you'd need to set it at to get 95% below that. These calculations are built in to Excel, and I've summarised them here in this spreadsheet, just using these built-in calculations. Firstly, know that if you're 1 standard deviation above the mean, then that's called the Z-score, a Z-score of 1. And the term Z-score in all kinds of applied statistics, social sciences, means how many standard deviations above or perhaps below the mean are you for any individual. So here if we have 1, that comes out as that 84% of the population, 0.84% of the population will be below that, 0.84 of the population. And the way this is calculated is using this formula in Excel, norms dist, type in norms dist and then just put in the number you're interested in. We change it to 2 standard deviations, 0.977. And these numbers here are just entirely from theory. Yet we can see the figures match very closely, the 0.977 and the 0.841 match very closely with the findings that we had. For 1 standard deviation was about 0.84, 2 was 97.7, instead of 97.7 we got 97.8 or 9, so it's very, very close. We put the 1.63 in, we get about 95%. In actual fact, here theory predicts 1.64. It's closer. Okay, well, so what? Well, if we look at the 2 pollutants that are normal, ignoring the one that isn't normal, and make a cut-off here, this was the one that comes out as 95% on each side. Because often we want to narrow our attention to maybe the top 1% or the top 5%. Or the bottom 5%, or the bottom 1%. So this is cutting off the top 5% and the bottom 95%. And in population 1, that's the cut-off level. Population 2, that's the cut-off level. Not very helpful because the numbers are so different. Because the sizes of concentration here and here are so different. That's not very informative. But once you, instead of looking at this as a number, you say, well, how many standard deviations above the mean here? And how many standard deviations above the mean here? Then it becomes interesting. because then you find in each case it's the same number of standard deviations, even though the numbers themselves are very, very different. It turns out that 1.63 will always give you this 5%, 95% cutoff. At least that's from the experiment. Actually, it should be 1.64, but it's close enough. Now, it doesn't work for pollutant 3. In pollutant 3, you'd need to have 1.90 standard deviations, which is not very helpful, because it's skewed. So the rule does not work for number 3. To summarise, here's some text, a bit boring with the rule, where in fact, for any data which is normally distributed, 95% of the population is less than 1.63 standard deviations above the mean, 1.64 in fact. The really powerful one, for any number of standard deviations, the same percentage of any normal population is less than that same number of standard deviations above the mean. So if I choose 2.05 standard deviations, the same percentage will be less than that number of standard deviations above the mean in any normal population. And it all works regardless of the level or the spread of the data, as long as the overall shape is normal. Z-scores are so useful that if you like formula, it's worth having a formula. It's very useful to know how many standard deviations above or below the mean any given value is, and this is the formula you get for it. It's called the Z-score. And all this is saying is you start from a number you're interested in, you take away the mean to work out how far above the mean you are, and then divide by how many standard deviations that is. So that's the mean of the population, that's the standard deviation of the population. In Excel, once you've got that normal, that Z-score, if you type in that formula, if you have a Z-score of 0.82, stick that in there, and it tells you what the percentage is going to be. Here's some examples. Now, the sort of thing that we apply this to in any kind of social science application or development application is, for example, we have one individual or one group, and you want to compare them with the whole population. For example, here, we may have one person and we're looking at height. We want to know, are they around average height, or, okay, they're bound to be a little bit off average height, because it's almost impossible to find someone who's exactly average. But say they're a little bit over, are they still quite close to the average, or are they really in the top few percent? So the kind of calculation you do here is this. Well, adult male height is what we're talking about. We know that the population mean is 1.75 metres. We know the population standard deviation is 0.076, so 7.6 centimetres. That measures how much variation there is from one person to the next. If you measure one particular man, and you find that they're 1.88 metres tall, clearly they're over average, but you can work out how far over average they are. How many people are going to be that tall? The Z-score comes out as 1.711. You can see how we got that in two ways. You could do it manually like this, using the formula, which is the Z-score is equal to the number you're interested in minus the mean divided by the standard deviation. So here, that means the 1.88 is the value we've measured. Subtract the mean, which is 1.75. That's about 13 centimetres, and then divide by the standard deviation, 0.076. That gives you roughly 1.711. Then, if you type that into Excel, let's get to Excel. Which it does finally. 1.711. 1.711. Then 95.6% of the population are below that, which means you're in the top 5%. So only 4.4% actually are greater than that, so into the top 5% of people, so really, really tall relative to everybody else. Some quicker examples then. If we're looking at fish, sort of calculation you might do here, if you're looking at tuna fish and you're maybe worried about what effects overfishing is having in a certain area, you want to keep track of the weights. You know that on average in this area, the population mean is 32.1 kilograms, standard deviation is this. You weigh a particular fish that you caught and find it's 12.6 kilograms. Obviously it's well below average, but how unusual is it? Is it bottom 10%, bottom 20%? Well, here's how you can work it out with the Z-score. You work out the Z-score in this way, or you can do it with you can do it all on the spreadsheet. If it lets us into it. Like this. The population mean is 32.1. Standard deviation 6.2. The fish that we've caught, 12.6, gives you a Z-score of minus 1.73. The Z-score is negative because we're below the mean here. So this number here will be smaller than this number, so negative. So a negative Z-score means that you're below the average for that population. Then if you look up the Z-score of 1.373, 14.2, 12.6, 1.373. You get 0.085. So only 8.5% are less than that. So down into the bottom 10% here. Interestingly, 1.373 should be the Z-score there, shouldn't it? Must have changed it somewhere. So the Z-score is minus 1.373, and you're in the bottom 10%. And finally, looking at crops, of course, horticulture, certainly parts of East and Southern Africa, is becoming quite popular now, flying flowers up to Europe. And some of the exporters are very strict about the flower sizes they'll accept. For example, you may have a specification on tulip width. So you may have 6.4 centimetre being the average width for tulip, standard deviation 0.31 centimetres. If you measure one particular flower and find it 6.5 centimetres, well, how does that translate to, how does that compare, that one flower compared to the population in terms of its size? Well, I can do the same calculation as before. Good. Let's work the Z-score out first. So we have 6.4 is the average, 0.31 the standard deviation. The one we've seen is 6.5, so Z-score is 0.323. Type it into Excel and it calculates that 0.627. So 62.7% of the population are less than that. So you're into the top 40%. You're quite near 50%, but just into the top 40% there. So the Z-score enables you to place one particular observation and say where does it rank in the overall population, given the information you have on the whole population. And it's used a lot in anthropometric studies, studies of horticulture, crop science, and studies of fisheries, among other things. Finally, I'll look at a comparison in the realm of BMI. Fewer pictures in this one. Imagine you've got the following data, which is data I got from the World Health Organization. Worldwide, for 6-year-olds, girls, mean body mass index is this, standard deviation is this. For boys, it's this. So suppose you're in a particular context and you find two individuals, 6-year-olds, a girl with a BMI of this and a boy with a BMI of this. Using the formula, you can convert these into Z-scores by using that as the X, that's the mean, that's the standard deviation, and the same for the girl. You find these Z-scores. So the girl, they're both below the mean, so they both have negative Z-scores, but the girl's got this negative Z-score, the boy's got that negative Z-score. So in fact, the boy's Z-score is bigger. The boy's a bigger negative score. When you work out in percentage terms, 41.4% of girls have lower BMI than that, but only 37.2% of boys have lower BMI than this. So the boy is nearer to the bottom of the distribution of male 6-year-old boy BMIs than the girl is. So relative